Welcome to month 2 of the Data Engineer track. Last month covered data platform strategy, the big picture thinking. Today you get hands-on with 2 foundational skills every data engineer needs: advanced SQL and dimensional data modeling. By the end of this session, you will have designed and implemented a complete star schema for a retail analytics scenario, written SCD logic, and produced analytical queries using CTEs and window functions. Everything runs locally in PostgreSQL via Docker. Here is the shape of your 4 hours. The first hour is lecture and demo covering advanced SQL patterns and Kimball dimensional modeling theory. Hours 2 and 3 are the challenge, where you design a retail analytics data model from scratch. Hour 4 is review and presentation, where you walk through your design decisions with the group. The challenge produces 4 deliverables: a star schema ER DDL scripts, SCD implementation, and 5 analytical queries. These are concrete artifacts that mirror real-world data warehouse projects. The skills transfer directly to Azure Synapse, Fabric, or any PostgreSQL compatible warehouse. There are 5 objectives for today. First, advance SQL fluency. You will become confident with CTEs, window functions, and upsets, the patterns you will use daily as a data engineer. Second, dimensional modeling using the Kimball methodology. You will learn to distinguish facts from dimensions and declare grain correctly. Third, star schema design, the de facto standard for analytical data models. Fourth, SCD implementation. You will write both type 1 override and type 2 history preserving logic in raw SQL. And fifth, analytical queries that join through your dimensional model to answer real business questions. Let us start with CTEs, common table expressions. A CTE is a named temporary result set defined with the with keyword. Think of it as a readable, composable building block. You can chain multiple CTEs, each referencing the previous one, to build complex transformations without deeply nested subqueries. On the left side of the slide, you see an example. First, we aggregate monthly sales into a CTE called monthly sales. Then we rank them by revenue in a second CTE called ranked. 2 steps, clean and readable. Compare this to the alternative, a subquery inside a subquery inside a where clause. CTEs win on readability every time. Now window functions on the right side. The key insight is that window functions compute a value across a set of rows related to the current row without collapsing the result set. Artigen by defines the grouping, order by defines the sequence within each group, and the frame clause controls exactly which rows participate in the calculation. The example shows a running total using sum with a window frame and a lag function that pulls the previous row's amount. These are the 2 most common patterns you will use in analytical queries. Other frequently used window functions include round number, rank, dense rank, and lead. One important note: prefer the rows frame over the range frame. Rows gives you predictable results by counting actual rows, while range can behave unexpectedly with duplicate values. Upsets are critical for data engineering. In PostgreSQL, you use insert on config to update. The key detail most people miss is the where clause at the bottom of the statement. You should only update rows when values actually changed. Without that check, you trigger unnecessary writes, bloat the write-ahead log, and fire update triggers on every row even when nothing changed. In Azure Synapse dedicated SQL pools, you would use merge syntax instead. The concept is identical, but the syntax differs. In Azure Database for PostgreSQL Flexible Server, or conflict works natively just like standard PostgreSQL. Now, 4 performance essentials to keep in mind. Explain analyze is your best friend. Always check query plans before attempting to optimize. Look for sequential scans on large tables, nested loop joins on big datasets, and significant mismatches between estimated and actual row counts. Indexing strategy matters. B-tree indexes handle equality and range queries. For composite indexes, put the most selective column first. Consider partial indexes for queries that always filter on the same condition. Partitioning is the single biggest performance win for time series analytical queries. Range partition your fact tables by date. Hash partition for even distribution across large tables. And for batch operations, use copy for bulk loads. It is 10 to 100 times faster than individual insert statements. Wrap batches in transactions and consider disabling indexes during very large loads, then rebuilding them afterward. Now we shift from SQL mechanics to data modeling theory. Ralph Kimball's dimensional modeling methodology has been the gold standard for analytical data warehouses for over 25 years, and it remains the right approach for most analytical workloads today. There are three core concepts to understand. Fact tables store measurable events, things that happened in your business. Each row represents one business event at the declared grain. Facts contain foreign keys pointing to dimensions plus numeric measures. Measures can be additive, meaning you can sum them across any dimension, like revenue. They can be semi-additive, like account balances, which you can sum across some dimensions but not time. Or they can be non-additive, like unit price, where averaging makes sense but summing does not. Dimension tables provide the descriptive context. They answer who, what, where, when, and why. Dimensions are typically wide tables with many text attributes and relatively few rows compared to facts. Conformed dimensions are dimensions shared across multiple fact tables. The classic example is the date dimension. Every fact table in your warehouse should reference the same date dimension. This enables cross-process reporting and consistent filtering. Look at the star schema diagram on the slide. The fact table sits in the center with foreign keys radiating out to each dimension table. This visual pattern is why it is called a star schema. The single most important concept here is grain. Always declare grain first. One row per order line item. Every design decision flows from that declaration. If you get the grain wrong, everything downstream breaks. Star schema versus Snowflake is one of the most common design debates in dimensional modeling. In a star schema, dimensions are denormalized. The product dimension contains category name directly as a column, even though that means repeating the word electronics thousands of times. The upside is simpler queries with fewer joins, fast aggregations, and better compatibility with BI tools like Power BI, which expect a star layout. In a Snowflake schema, dimensions are normalized into subtables. The product dimension joins to a category table, which joins to a department table. There is less data redundancy, but you pay for it with more complex queries, additional join operations, and a steeper learning curve for analysts. Looking at the comparison, query speed favors star, storage favors Snowflake, and ETL complexity favors star. But here is the key insight. Storage is cheap today. The small savings from normalization rarely justify the added query complexity. The recommendation for most teams is to start with the star schema. Only move to Snowflake when you have a specific need, such as a dimension with millions of rows where redundancy becomes a real storage or update concern. Azure Synapse specifically optimizes for star schemas. You hash distribute your fact table across compute nodes and replicate your small dimension tables to every node. The query optimizer handles this pattern extremely efficiently. Slowly changing dimensions handle the reality that dimension data changes over time. A customer moves to a new city. A product changes categories. How do you handle this in your dimensional model? There are three types, each with different trade-offs. Type 1 is the overwrite approach. Simply update the row in place. The old value is gone forever. Use this for corrections like fixing a typo in a customer name or updating an email address. It is fast and simple, but you lose all history. Type 2 is the new row approach, and it is the workhorse of dimensional modeling. When an attribute changes, you expire the current row by setting is current to false and valid to the current timestamp. Then you insert a new row with a new surrogate key. The updated values is current set to true and valid to set to a far future date like 9/9/1999 to 12/31. The old row remains in the table. You can query what a customer's address was last year, last quarter, or at any point in time. This is essential for any attribute where historical accuracy matters. Type 3 adds a previous value column. It only tracks one prior state and is rarely used in practice. For the challenge, you will implement both type 1 and type 2. The critical thing to understand is that type 2 only works with surrogate keys. When your fact table joins to the customer dimension on the surrogate customer key rather than the natural customer id, historical facts automatically point to the correct version of the customer record. Time for the main event. You are going to design a dimensional data model for a mid-size retailer with 50 stores. Here is the scenario. You have 4 source systems. Orders and order items contain the transactional core with order id, customer id, product id, store id, quantity, unit price, and order date. Products and categories contain the product catalog with names, SKUs, categories, subcategories, brands, and prices. Customers contains the customer master with names, emails, addresses, regions, sign-up dates, and loyalty gears. And stores contains the store directory with locations, formats, and manager assignments. The challenge has 4 parts, each building on the previous one. Part 1 is source analysis, where you profile the data and declare your grain. That is 25 minutes. Part 2 is star schema design, where you write DDL for your fact and dimension tables. That is 35 minutes. Part 3 is SCD implementation for DIM customer. That is 30 minutes. And part 4 is writing 5 analytical queries against your model. That is 30 minutes. You have 2 hours total for the challenge work. Let us dig into the first 2 parts. For part 1, source analysis, start by profiling your source tables. Non-count and count distinct on every key column. Check for nulls. The goal is to understand cardinality. How many unique customers, products, and stores do you have? Are there data quality issues you need to handle? Then declare your grain. For this model, the grain is 1 row per order line item. Verify this by checking that the combination of order id and product id is unique in the order items table. If it is not unique, you need to understand why before proceeding with your design. Finally, map every source column to its destination. Decide which columns become fact measures, which become dimension attributes, and which serve as foreign keys. For part 2, star schema DDL, create your dimension tables first. Build DIM customer, DIM product, DIM store, and DIM date. Always use surrogate keys with serial or big-serial. Include SCD metadata columns on dimensions where you plan to track history. Is current, valid from, and valid to. Then create fact sales. All foreign keys in the fact table must reference surrogate keys, not natural keys. Add not null constraints on every foreign key column. A missing dimension link is an ETL bug, and your schema should catch it. The example DDL on the slide shows DIM product with SCD columns at the bottom. Use this as a template for your other dimensions. Parts 3 and 4 are where you bring the model to life with working SQL. For part 3, SCD implementation, you will write both type 1 and type 2 logic for DIM customer. For type 2, follow the 2-step pattern shown on the slide. First, expire the current row by setting is current to false and valid to the current timestamp. Second, insert a new row with the updated values is current set to true, valid from set to now, and valid to set to the far future sentinel date. Always wrap both steps in a single transaction. For type 1, simply update the field in place on the current row. Use this for email corrections where you will not need history. Test your implementation with sample data. Update the customer's address, then query the table to verify you see 2 rows, 1 expired and 1 current. For part 4, write 5 analytical queries that demonstrate your model works and answer real business questions. Query 1 calculates monthly revenue trends with month-over-month percentage change using the lag window function. Query 2 ranks the top products within each category using dense track. Query 3 computes customer lifetime value as a running total. Query 4 compares each store's performance to the regional average using AVG over partition by. And Query 5 performs basket analysis with entire quartile bucketing. Remember the critical rule, all joins must go through surrogate keys. Whenever join fact sales to DIM customer on customer id, always use customer key. This is what makes SCD type 2 work correctly. Here is a deep dive on the date dimension. the most universal conform dimension, and one that is often done poorly. The DDL on the left shows the complete structure. Notice the integer primary key using YUMDT format. This enables readable where clauses like date key at green 202050 10 on 2020 and it supports efficient partition pruning. The generator query uses PostgreSQL's generate series function to create every date from 2020 through 2030 in a single insert select statement. This is a one-time setup that takes seconds to run. Key attributes to include day name and month name for human readable reports, is weekend, and is holiday for filtering to business days, and fiscal year and fiscal quarter for financial reporting, since many organizations have fiscal years that do not align with calendar years. In Azure Synapse, always replicate dim date across all distributions. It is a small table with only a few thousand rows, and replicating it avoids expensive data movement during joins with hash distributed fact tables. One important best practice: never compute date parts on the fly in your queries. Extracting month or year from a date column forces table scans and prevents the optimizer from using statistics effectively. Always use the pre-computed columns in your date dimension instead. Let us review what you need to submit and how it will be evaluated. There are 4 deliverables. First, a star schema ARD showing your fact table, all dimensions, relationships, and green declaration. Second, complete DDL scripts that create all tables with proper constraints and indexes. Third, working SCD implementation with test data demonstrating both type 1 and type 2 patterns. Fourth, 5 analytical queries using CTEs, window functions, and proper surrogate key joins. Assessment is weighted across 3 areas. Data model quality counts for 40%. This includes correct grain, proper surrogate keys, conform dimensions, and appropriate SCD choices. Skill proficiency also counts for 40%, covering clean CTEs, correct window function usage, working upserts, and functional SCD logic. Presentation counts for the remaining 20%, evaluating how clearly you explain your design decisions and trade-offs. That wraps up month 2. Today you built a complete dimensional model from scratch, from source profiling through analytical queries. These are the same skills you would use building a data warehouse in Azure Synapse, Databricks, or any PostgreSQL compatible platform. Next month, you move to ETL and ELT pipeline development. You will build batch pipelines, work with orchestration tools, implement data quality checks, and develop testing strategies. The dimensional model you built today becomes the target for next month's pipelines, so keep your scripts handy. Thank you for your work today, and see you in month 3.